So we want to provide high-performance ZK proofs and at the same time provide seamless developer experience. We see a future where you don't have to do anything different just because you want to have a ZK proof for your Rust program. I think a lot of the current efforts in ZKVMs are very focused on Ethereum. OpenVM is the first integration that we have with Powdr, so any ZK proofs that are made with OpenVM can automatically make use of Auto-Precompiles.
Precompiles. The term will sound familiar to any developer writing code day in and day out. But imagine how much simpler life could be if those precompiles were automatically synthesized. Yes, that's what we are going to explore today, end-to-end auto-precompiles. Welcome back to Ecosystem Project Demo. This is episode 26, brought to you by ECH Institute. I am Pooja Ranjan, joined by Akash from our team. Today, we are talking about Powdr, a project introducing an approach to automatically synthesize precompiles for ZKVMs. It shares end-to-end proof generation, performance number, and aims to make developers' life easier. What is this project, and how is it impacting the Ethereum ecosystem? To unpack it all, we are joined by Leo. Leo, welcome.
Thank you. Great to be here.
Leo, please tell our listeners a bit about yourself and your journey in the Ethereum space before we get into the presentation.
Yeah, sure. Yeah, my name is Leo. I'm one of the founders of Powdr. So this is a project that started within the Ethereum Foundation in 2023. And late last year, we spun out as our own organization and basically trying to push for better ZK tooling in the ZK ecosystem. Before that, me and the other founders, we were working at the Ethereum Foundation for a long time. I first joined as a Solidity core developer, and then I was leading the formal verification team for the longest part of my time at the EF.
That is awesome. So you already have experience of core development and things that come on the way of core developers. All right, this is pretty interesting background. Thank you so much for sharing. I understand there is a small presentation, so let's get into the presentation right away.
Yes. Yeah, so this is a very short presentation on the main things we're doing at Powdr and with Powdr. So the high level idea of what the things we want to do as a group, as a team, is to improve ZK tooling or improve developer tooling in the ZK ecosystem. At the same time as we want to improve proof generation performance, which is also a lot of people's goals. So we want to do these things at the same time. So we want to provide high performance ZK proofs and at the same time provide seamless developer experience. And a lot of the work we do is kind of in the middle of, we don't do, for example, ZK prover work, where we prover code ourselves or ZK research or cryptography research per se. We work more on the compiler layer, where we have access to different programming languages and different VMs, different paradigms, and we do this connection from high-level code or circuit code to ZK provers. And ZK provers have different types that can be optimized in different ways. So basically, we build this bridge that lets people make ZK proofs in a highly performant way without compromising developer experience. So of course, this is a common topic in ZKVMs. That's one of the main reasons ZKVMs exist. So people didn't want to write ZK circuits anymore because they're difficult to write, they're difficult to audit, they're difficult to maintain. And at the same time, you need a team of experts. It doesn't scale a lot if you're just writing circuits all the time. With ZKVMs, you can basically make proofs for Rust or even Go programs. You can reuse a lot of the code you already have, so you don't have to rewrite things from scratch in a new DSL, a new language ecosystem. With that come different challenges. So ZK proof performance has higher requirements when you're making proofs with ZKVMs as opposed to just standalone circuits. But yeah, so there's a lot to do in the intersection of these two things. And this is where the main chunk of our work exists. And the two main things we work on are Auto-Precompiles and Womir. So the main thing currently is Auto-Precompiles. So what does that mean? So ZKVMs, for example, if you take into account RISC-V ZKVMs, you can make proofs for RISC-V programs, which usually come from Rust or C++. But the base ZKVM can have a lot of overhead in proving because it has to be generic over the instruction set. And if you're thinking about things that like Ethereum needs a lot when you're verifying Ethereum block, there are things like catch like hash ECDSA, signature verification for every single transaction that you have to do. These are pretty expensive things to prove if you're just going through RISC-V code. So usually if you did this in a circuit, you would have personalized or like customized code that verifies those things specifically, and then you get better performance out of this. In ZKVMs, these are precompiles. These are not the usual Ethereum precompiles. They're still called precompiles. These are handwritten circuits that are more than running the same thing over the software version that gets compiled to RISC-V. And these circuits are usually, they have a similar developer experience to the old style circuits people don't want to write anymore now that ZKVMs exist. You still have to write them manually. They're big, they're difficult to write, difficult to audit, difficult to maintain. The process of writing these circuits doesn't really scale. So you have to do it manually. You need expert knowledge. So it's not very productive to just keep writing these things by hand. With Auto-Precompiles, which is a library that we built inside Powdr, which has a different toolkit for ZKVM acceleration, this module basically builds, it synthesizes these precompiles from the guest program automatically. So the developer doesn't have to write precompiles. These circuits are generated automatically just from the program you're trying to prove. So if we take a Rust program that's trying to do Ketchak computation, even if it doesn't have the manual precompiled in Ketchak, the manual circuit, this module will see that Ketchak as a heavy piece of computation in this benchmark and will synthesize a circuit using the original code, but then optimizing it a lot that does the same thing, but in a much more optimized way for the ZKVM. And this approach is agnostic to ASA, it's agnostic to ZKVMs. It's agnostic to the program. It can accelerate any guest program that you want to make a proof for. And here are a few links. So this is the main repo where we have everything. And these are 2 blog posts we wrote on, first on the technique itself and how it works, and then on integration that we did with OpenVM, which is a high-performance ZKVM that has access to Auto-Precompiles as well. And then we published some performance numbers, which I can also show here. So just wanted to quickly mention this. This is the blog post where we go through the technique, have a benchmark on Ketchak. So you can see, for example, here. So this row here is what you get if you just make a proof for the RISC-V program that does Ketchak. There's no manual precompile, it's just Rust doing Ketchak. You can see it's not very optimized. It's very slow compared to the other rows. And this row here is when you add the manual precompile. This is about a couple thousand lines of Rust code, complicated circuit, difficult to audit, and so on. But of course, it's very performant. So it reduces the time to make this proof by 12x, basically. So you can see it's worth it, right? So if you're doing a lot of Ketchak computation, which Ethereum does, you will want to have the circuit anyway. And in the latest iteration we have, or that we ran the benchmarks, with Auto-Precompiles, you can see that it actually accelerates the benchmark even more than the original manual circuit. So this circuit here does the same job as the circuit here. It's not exactly the same. They have a few differences, but mostly. And you can see that it provides more acceleration than the manual circuit that was written before. So this is basically like in simple terms, what we want this approach to do. It's 2 things, basically provide better security, developer experience, and performance to the alternative, which is writing manual precompiles. But at the same time, there are manual precompiles written for things that a lot of people care about, which is Ketchak, ECDSA, and so on. But if you have a Rust program that has some heavy computation that not a lot of people have, therefore people haven't written precompiles for them yet, you're going to have a hard time writing the precompile yourself. So this approach is especially powerful for cases where people have not written manual precompiles for. So you can see here that it's actually almost 13 times faster than the pure software version. And the main thing is that this is actually agnostic. This is not specific to Ketchak. If you put different guest programs that don't have manual acceleration via manual precompiles and manual circuits, you still get some acceleration without actually doing anything. So, and the reason why we do this kind of optimization is that a lot of the optimizations that are performed in ZK space, they come from the cryptography side of things. So you have faster provers, faster research that leads to newer research that leads to faster provers and new techniques. But there's also a lot to be done on the compiler side, on the program side, that often gets kind of overlooked because we have Rust, we have LLVM, how come these programs are not optimized? They are optimized for what they're compiled for, which is not ZKVMs. So when we use these programs in ZKVMs, the cost model is completely different. So the cost model of ZKVM is very different from the hardware where these programs are going to run. So by combining the compiler optimization knowledge with the specific domain knowledge from ZKVMs and the circuits, we see that there's a lot that can be done to accelerate these proofs on top of any performance improvements we get from the prover. So this doesn't replace the prover. So these things compound, and these are orthogonal to prover improvement. So you can actually do both at the same time and improve many times the performance of the prover. So the other main project that is slightly unrelated, but eventually will be related, is this project called WOMIR, which means write once memory IR. The name is not final, but we're going with this for now. And it's a compiler from WASM to a ZK-friendly ISA. And you can see this as, for example, an alternative to the RISC-V pipeline that a lot of ZKVMs use. So instead of compiling Rust to RISC-V and transpiling to whatever the language of the ZKVM is, we compile to WASM, which we can reuse all the compiling infrastructure for. Then we compile to the ZK-friendly ISA that is one step lower than WOMIR, but the main point here is that it has a special memory region, which is write once, and this is inspired by Cairo VM, which can bring a lot of performance improvements together with the compiler work, because it's another example of compiling a program for what it's going to be used, or for where it's going to be used. So it doesn't make sense to compile WASM to a write once memory if the ZKVM doesn't have a write once memory. It also doesn't make sense for the ZKVM to have a write once memory if the compiler has no idea about that and doesn't make use of this. So the idea here is that we have, or we will have at some point, the write once memory implemented in the ZKVM. At the same time, the compiler knows about that. So we can actually take WASM and optimize WASM specifically for the ZKVM with write once memory case, which can give a lot of different performance optimizations that are just not available in RISC-V for different reasons. And with this, we're also working on integration with OpenVM. And because OpenVM is pretty modular and it's easy to extend with different instructions and new instruction sets, basically. So we're writing this new ZK-friendly instruction set, which is really only a few more instructions than OpenVM currently has with RISC-V. Then we can compile Rust or C++ or Go to WASM, to WOMIR, to this ISA. And the idea is that we get ZK-proof performance improvements by having a better complete pipeline with more efficient ZK primitives and a compiler and an optimizer that knows about these and can make use of them, instead of just being a completely generic pipeline that doesn't know about things that can be optimized if you are compiling for a ZKVM. So this is the link to the IR itself and the ISA, and this is the integration with OpenVM. So yeah, so you can see a lot of our work, or most of our work, not always, is basically working on compilers, building compilers, adjusting compilers, and optimizers from high-level programming languages to provide the best developer experience for people that want to make proofs for their programs, and at the same time trying to make this as optimized as possible so that the ZK proofs are very performant.
Thank you. Thank you so much for sharing these. I mean, you took me down the memory lane. I remember hearing about eWASM team back in 2019, but beyond that, it was not too much into active discussion when we are discussing Ethereum and upgrades. It's really interesting to learn that team was working in the background, and now we have contributors coming out with individual project ideas and trying to support the ecosystem in multiple ways. I also love the agnostic approach. So it's not going to be limited to Ethereum only. We can look into the growth of the Web3 ecosystem altogether. So that is great. Thank you once again for sharing that. You have covered a lot of things. My questions could be repetitive, but I want to just have some better understanding of things where we are from a high level perspective. So my first question to you is about the main motivation. You talked about multiple ideas. It could be security, it could be better developers experience and performance for prover. What do you think was the main motivation to design the project Powdr?
So the main motivation, I would say, is the lower part here, the seamless developer experience. So that was at least a driving force, because there's also a bit of a delay. And so if you think about how programming languages are used now, the people are coding C++, Rust, Python, Go, etc. And you don't see that much or that often anymore that people are writing pure assembly code to optimize whatever they are trying to do, as they used to 20, 30, 40 years ago. I don't know exactly. But this still is the case in ZK development, because it takes a while for the research to become production software, to become developer experience, and so on. And obviously, a lot of normal software development has been done decades ago. So it's natural that ZK tooling is a bit delayed, but we don't see why it has to be the case forever. And I'm sure a lot of people agree with this, that there are a lot of people working on the same goal. And yeah, so we see a future where you don't have to do anything different just because you want to have a ZK proof for your Rust program. So it doesn't matter if I'm encoding Rust to run on my server, to run on my laptop, to run on a GPU farm or whatnot, or to make ZK proofs, or I don't know, whatever other use case. You shouldn't have to. It still is the case. I think this is still a very futuristic thing, but I do believe that one day developers won't have to care anymore that they're doing 4ZK proofs or to run natively or to run on the phone, or etc. They will just write code and you get a ZK proof as outcome.
Very interesting. So if I have to understand about this project, it seems like Auto-Precompile is one of the most powerful feature of it. When preparing this Auto-Precompile, who was the main target audience in mind? Meaning, was it the core developer or was it the guest developer? Assuming that people want to have projects open source and invite a lot of participation.
Yeah, so on both sides, it's basically both users and ZKVM developers. So the direct users of the code are the ZKVMs, because they need to integrate the module. They need to basically use Auto-Precompiles in their internal circuit building. But there's different ways. So for example, in OpenVM, because they have a modular and extensible framework, it's actually possible for direct users of OpenVM to use Auto-Precompiles without having to change anything in OpenVM. So, and this is not only related to Auto-Precompiles, it's related to OpenVM's architecture itself. So they've built it in a way that you can import the normal base OpenVM, and you can extend it with your own circuits if you want, with your own instructions, with your own precompiles. And as part of these, this can also be the Auto-Precompiles. Right, so there's two sides here. So on one side, I would say it's for end users that want to accelerate programs that don't have precompiles for yet, and that they don't have the expertise or they don't want to spend the time building precompiles manually. So they can just plug that in, they should get acceleration, just like that. The other side is ZKVM developers. And this is a bit more like cutting edge related. So it's like, how can we extract the maximum performance we can out of the whole system? So can we use a mix of auto-precompiles, manual precompiles, software version? It's almost like a piece of research as well. So how can we extract as much as we can from this proof? And this currently is especially important for Ethereum real-time proving for the L1. So there is this, I'm not sure how decided it is. It feels very decided, but I'm not sure. I don't speak for Ethereum protocol, but it might be the case that in a couple of years, there's this Ethereum snarkification going on, where instead of having a lot of validators, we're going to have ZK proofs that are verified by a lot of people. These proofs are very heavy to make. So currently, the ZKVMs that do provide real-time proving, they use a lot of GPUs, and they use a lot of manual precompiles to achieve the desired performance. So anything we can do to improve that further, even if it's a little bit, is already very, very important for Ethereum, because there's still a lot of improvements we have to make to get to the point where Ethereum would be snarkified. We're not there yet. So in that sense, Auto-Precompiles can also be seen as a piece of research that's further accelerating the state of the art in ZKVMs.
That is cool to know. I mean, it is on the roadmap or on the horizon for the ecosystem. So perfect. We are going in the right direction. It seems like the project is definitely going to help out in saving time, in coding time. Do you think that it is also going to significantly optimize in economical sense? The proofs would be more economical now.
Yeah, I think this really, like, the time and the computational effort you take to make a ZK proof translates directly to costs, right? So these machines are not cheap, or I guess some of them are, but like, especially if you think about the other problems people would have to solve with Ethereum sanctification. So currently, to get the real-time proving, let's say we need 10 GPUs, 20, 40 GPUs. Not everyone is going to have that. So currently, one of the things that exists for Ethereum is home circuits, right? Home validators. So this will likely not be possible if we require many GPUs to become a prover for Ethereum. Necessarily exactly what you asked, but just to draw a parallel between the costs. So if we need 40 GPUs, it's only the cost of having the machine or renting the machine, but it's overall the cost of also building the whole thing, right? So with precompiles, you also spend a lot of developer time actually writing the code, auditing the code, maintaining the code. And this is both time and costs, and time and direct, like financial costs. The former, it's quite direct. So you want to generate more proofs, you need to spend more time in these machines. It's going to cost more, either by owning the machines or by renting servers or GPU farms. So I would say there's these two sides, these two economical sides to the question.
Yeah, that is interesting. Of course, I think as the technology is evolving, we are trying to make it more faster, more economical, so that it can be more decentralized at the end of the day. Having these technologies in place are helpful. My next question to you is with respect to the applications and maybe the early adopters. By any chance, you came across any project team or any low-hanging application ideas in your mind that you would like to share with people, or you have met any early adopter of this technology yet?
Yeah, so for now, I think a lot of the current efforts in ZKVMs are very focused on Ethereum. So yeah, it feels like a repeated answer, but it just is the case that there's so much money and effort being put on real-time ZK proving for Ethereum block verification, which already happened before. So you already had ZKL2s before that had similar proofs to Ethereum verification. But now there's really big effort in making proofs for L1. Yeah, so OpenVM is the first integration that we have with Powdr. So any ZK proofs that are made with OpenVM can automatically make use of Auto-Precompiles. And so, for example, the ETH proofs initiative, I think OpenVM is not there yet, and we're not there either. But it is one of the goals we have, is to basically support Ethereum certification by providing proofs for its proofs as well. But yeah, so I would say for now, basically the OpenVM ecosystem is the easiest way to get access to Auto-Precompiles.
That's pretty cool. In terms of challenges or maybe the blockers, what are the biggest challenge or blockers that you think are stopping the adoption of ZK as such in the present scenario?
I think one thing, it's a difficult topic. There's a lot of very smart people working on it, but it's still a challenging field in itself. The research is complicated, implementations are complicated. It can take a while for a paper to translate into the code. And many times when it does translate into code, it doesn't actually work in practice as people would expect. This actually happens a lot. And then when a paper comes out, you're not sure, there's a lot of promises, but you're not sure if it's actually going to translate into practical performance or different features. So I think that combined with the lack of tooling, and it's kind of like a cycle in a way, because the reason why tooling is not more established in parts is because you're not sure which ZK attack is going to win. So do you focus on Starks? Do you focus on Snarks? Do you focus on folding or different things? And it's not easy to make tooling that is generic over all the possible ZK pieces of technology. So you kind of have to bet on something. And the moment that you do, you try to build better tooling for that specific niche, which is one of the things we're doing. So most of what we do actually works well with the AIR arithmetization used by Starks, which is what OpenVM and other ZKVMs use for what they call the core or app proofs. So for example, if you wanted to translate Auto-Precompiles for like a Snark folding scheme, it would not be trivial because we went on the AIR Stark path. Yeah, I think it's kind of like a cycle of, it's a difficult field. You don't know which ZK attack is going to win. You don't know what papers are going to work. So you refrain from making super generic tooling, which is also difficult to build in the first place. I think it's just that's delayed. I think tooling is definitely getting better every year. We have better and better tooling, better ZK DSLs, and circuits are back in a way with great projects focusing on circuits again, but only ZKVMs, which is also nice to see for client-side proving, for example. Yeah, I think a mix of a few different reasons.
Yeah, and I think ETH Proof team is doing great in having these calls weekly by weekly. As it grows, people will also start thinking about different tooling that can support the ecosystem as it is growing. Well, I would like to pick your brain on the EIP proposal, which is of a block level access list. Yeah, EIP 7928. We had a meeting this morning and I was intrigued by hearing that we can perhaps use BAL for ZK trace generation, and it will be a nice idea to do that. Though we understand that production may not be in momentum because ZK trace is like a little far from actually being produced on mainnet, but I want to hear from you. What do you think about this proposal, and do you think this would help the work that you guys are doing here?
I'm not familiar with the EIP, so I would have to take a look. So what's the number?
7928. I mean, it came on general discussion. That's why I thought of checking it with you. Like, it seems like using BAL would be making proofing easier for ZK proofs.
Oh, is it for to do parallel trace?
Yes, I guess so.
Right. Yeah, that makes sense. I mean, Succinct did something. I don't know if it's maybe it's actually the same thing. I don't know if it's exactly the same thing, but when SP1 first presented the real-time proving that they had it on top of like a parallel block execution, which basically enabled the proofs to be parallelized a lot better on GPUs. So because if you have to sequentially execute everything to build the witness data and then spawn parallel proofs, you lose that there's time that you could have gained by pipelining the trace generation before, like while spawning different provers, which is what they did, I think, for their first real-time proving benchmarks. It might have been this EIP. I haven't been following EIPs too closely, but I think it might be the same. I don't want to say that it is, but if it's not this one, it's probably a similar related one.
Right. Yeah, I do not want to get into the technical details of it. I was just wondering if it was even discussed in the community that people are trying to bring such proposal on Ethereum mainnet may be helpful for ZK people.
Yeah, I think, again, if it is the same thing that I'm talking about or similar, then it would definitely help a lot.
Very cool. Well, my next question to you is about community contribution. How do you think that general community may able to contribute to Powdr's roadmap or even in the adoption? Anything as a call to action that you would like to share with them?
Yeah, I think integration and benchmarking is a really good way to get feedback on what people want and need. So it's difficult to say upfront which optimizations we should be implementing or which features we should be implementing. And this is ultimately an infrastructure project. So it's difficult to go and ask people exactly what, because we don't necessarily talk or work with end users frequently. So a lot of the people we talk and work with are ZK developers or ZKVM developers or researchers. Often it's difficult to be accurate about what's the very next thing we should be working on. And usually these things come from benchmarking, but benchmarking requires integration. And we are definitely interested in integrating these two different techniques to different provers. So for example, one idea with Omir is to integrate different provers that may support reference memory, or for example, circuit languages could be an idea as well. As well with Auto-Precompiles, it can integrate with almost all ZKVMs, or different projects. Doesn't have to be ZKVMs. It can also be ZK DSLs. It can be circuit languages. I think this could be very useful as well. And even related to what you asked before about adoption, one thing I forgot to mention, it's not only Ethereum or Web3. There's a lot of work outside of Web3 or blockchain that goes in a similar direction. I don't know if you've seen the Google results from a few months ago. So they have some ZK proof support in the Google Wallet now. And this was done completely in-house by two researchers at Google. And we had contacts with different foundation people, with different ZK researchers. And the tools that had been built before just didn't work for their use case, which was age verification on the phone. So they wanted to make proofs that you were older than 18 on your phone. And for this, they needed a very specific setup. They wanted to be able to parse your passport or driver's license or something locally on the phone and make a hash of it and make a signature verification. That's all. And with existing things that we had in the ZKVM world, even the circuit world, just wasn't enough for them. They did reuse some literature, ZK protocols, but not the tooling that we had for other things. So I think the adoption is actually much larger than when we think about ZK in terms of Web3 or Ethereum or Bitcoin or L2s. Yeah.
Yes, of course. Sometimes we can have tunnel vision and just focus on Ethereum ecosystem, but there are other development and adoption going on. Glad to know about this one. Well, I would like to hear from you. How do you see Powdr evolving compared to other ZK projects? There are multiple projects, and I understand that ZK is going to be one of the most active conversation projects and applications those are being developed. So what do you see? Where do you see Powdr to be standing there?
Yeah, so we do want to keep basically going in this direction. So seamless developer experience has always been our focus and the main thing we want to provide for people, also based on the expertise that we have in the team. At the same time, also aiding high-performance ZK proofs. So I think what I see mostly is to continue providing better and better tooling to get to this goal here where people don't even notice they're making ZK proofs. And it just happens. They just open some software somewhere and it just happens that it makes a ZK proof for them, happening either on a server, on their phone. This is, I guess, technical implementation detail, but that's the seamless part for developers and users. So I think this is the part where ZK proofs just become a library, just become an API call that you make, and then you get a proof and someone else can verify it. I think this is the direction that we want to keep pushing. And at the same time, we love to collaborate with different teams. We have collaborated and we're still collaborating with different teams working on different things like ZKVMs or VMs or Ethereum protocol or different compilers. And this is basically how I would see it. So continue pushing the seamless developer experience direction while collaborating with other teams that are building different parts of the puzzle.
Very interesting. You have briefly mentioned how you want to see the ecosystem getting involved around zero knowledge. If everything goes right, what does success look like for Powdr in like 5 to 10 years from now?
That's a very good question that I would like to have the answer for. I would say that one of the Powdr compilers in the Powdr toolkit is one of the main compilers being used by Web3 and non-Web3 developers out there.
Maybe one of the most used compiler.
Hopefully, yeah.
Very well. Thank you so much, Leo, for sharing all this information about this project. It seems pretty interesting. It seems that it's definitely going to ease off burden of developers who are sometimes kind of reinventing the wheel and trying to get into the complex codes of precompilers. This auto-precompile might relieve them and help them do the coding faster, and we can see the project simpler and sooner.
Yeah, thank you. Thanks for the chat and thanks for the great questions.
Very well. I'm so excited for seeing the adoption growth, and we hope that new applications which are coming across Web3 should also adopt it. Thank you so much for your time once again, and we hope to see you around.
Thank you.
All right, dear listeners, you will find all the links and resources in the episode description. If you enjoyed this conversation, please share it with another developer you know. Helping your fellow builder is how knowledge spreads. That's how we can make our ecosystem even more robust. We'll be back with another exciting ecosystem project demo. Until then, keep learning and keep building, keep sharing your knowledge with people, and keep shaping the future of Ethereum. Cheers, everyone.